What would happen if the invisible structure holding the entire universe together became visible for the first time? Have you ever thought about that? For decades, dark matter has been one of science's greatest mysteries. We know dark matter exists because of the gravity that shapes galaxies, but we have never been able to see it directly. Now, using the James Webb Space Telescope, scientists have created the most detailed map of dark matter ever made, revealing the hidden cosmic web that connects everything in the universe. Published in the January 2026 issue of Nature Astronomy, this discovery shows us the invisible skeleton of reality. Let's now examine what they found and why it changes everything we thought we knew about the formation of the cosmos. The research was conducted by Diana Scognamiglio at NASA's Jet Propulsion Laboratory in collaboration with an international team that included astronomers from Durham University and École Polytechnique Fédérale de Lausanne. Their success represents a fundamental leap in our ability to see the invisible. Using Webb's unprecedented sensitivity, the team analyzed approximately 800,000 galaxies in a region of space known as the Cosmos Field, located in the Sextans constellation. This area had previously been studied by Hubble and ground-based telescopes, but Webb's capabilities allowed scientists to see details that were previously impossible to detect. The map does not directly show dark matter, because dark matter does not emit, absorb, or reflect light. It passes through ordinary matter like a ghost. However, it does something that cannot be hidden. It exerts gravity, and gravity bends space itself. As light from distant galaxies travels through the universe toward Earth, it passes through regions filled with dark matter. The gravity of dark matter bends space-time, warping the light and distorting the shapes of distant galaxies. This effect is called a gravitational lens, and it plays a key role in seeing the unseen. By measuring how the shapes of hundreds of thousands of galaxies are subtly distorted, scientists can work backwards to reconstruct where dark matter should be. This is similar to detecting an invisible object by observing how it affects everything around it. Webb's extraordinary resolution allowed the team to measure these distortions with unprecedented sensitivity and achieve twice the angular resolution of previous dark matter maps. The result was striking. The map reveals dark matter not as randomly scattered clusters in space, but as a vast, interconnected cosmic web. Dense dark matter clusters are connected by long, thin filaments, forming a structure that spans millions of light-years. These are not theoretical predictions or computer simulations. They are reconstructions based on actual observations of real galaxies. What the map shows is profound. Dark matter and ordinary matter follow the same structural patterns. Where galaxies cluster together, dark matter densities mirror their distribution. Where galaxies form narrow bridges between clusters, dark matter forms the same connections. This is no coincidence. It is direct evidence of how the universe formed. According to cosmological models, dark matter first gathered together in the early universe. The gravity of dark matter created wells in space-time that pulled in ordinary matter. Gas and dust fell into these gravitational wells and eventually formed stars and galaxies. In this way, dark matter determined the large-scale architecture of the cosmos. Galaxies did not form randomly. They formed in the locations dictated by dark matter. What do you think about this? The new Webb map confirms this model with much more detailed observational evidence than previously available. Physicist Richard Massey from Durham University, a co-author of the study, describes it as a gravitational skeleton into which everything falls and transforms into galaxies. The map shows that this process occurs on cosmic scales. It reveals how the universe is structured not by what we can see, but by what we cannot see. The scientific value of this is enormous. Researchers can now test structure formation models with much higher precision using real data. The shapes of dark matter halos, the density of filaments, the mass distribution within clusters, all of these can be compared with theoretical predictions. Cosmology is shifting from model-driven interpretation to data-driven verification. While scientists still don't know what dark matter is, they can now explain what dark matter does with extraordinary clarity. This creates a fascinating paradox. Dark matter is being mapped structurally, in increasingly greater detail, yet its physical nature remains entirely unknown. It does not interact electromagnetically. It does not emit radiation. Its presence and effects are known only through gravity. The dominant form of matter in the universe, comprising about 85% of all matter, is also the least understood. Scientists can see its effects everywhere, but they cannot detect a single dark matter particle. The Webb map also reveals structures that were invisible to previous telescopes. Gavin Leroy, a postdoctoral researcher at Durham who co-led the study, explains, "Previous maps were like looking at dark matter through frosted glass. Now we see the universe more closely and more clearly." Webb detected features such as faint filament bridges connecting low-mass galaxy groups and larger structures. These had not been detected before because the relevant galaxies were too distant or too faint for other telescopes to resolve clearly enough. The observations required 255 hours using the Webb telescope's near-infrared camera and mid-infrared instrument. Designed and managed by JPL, MIRI was particularly valuable because it could detect galaxies hidden by cosmic dust clouds, adding galaxies to the map that would otherwise be invisible. The team also used data from at least 15 other ground-based and space-based telescopes to measure distances and enhance the map's accuracy. This represents a global collaborative effort in cosmology. Its implications extend beyond astronomy. By shaping where the first stars formed, dark matter influenced the formation of heavier elements and complex chemistry. These processes made the formation of planetary systems possible. The stable environments where life could emerge depended on structures created by dark matter billions of years ago. In this sense, dark matter is not just a cosmic curiosity. It is part of the causal chain that made the formation of Earth possible. In the future, the Webb map is only the beginning of a new era in dark matter research. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in late 2026, will map dark matter across much larger regions of the sky. Although Roman will not achieve Webb's spatial resolution, it will provide statistical data showing how dark matter was distributed in different cosmic eras. The European Space Agency's Euclid telescope is already conducting similar research in orbit. Ground-based projects such as the Vera C. Rubin Observatory, which will release its first images in 2025, will also provide complementary data. Together, these missions will transform dark matter research from isolated snapshots to continuous evolutionary maps. Scientists will be able to track how dark matter structures have grown from the early universe to the present day. This will test cosmological models in ways previously impossible. It will also constrain theories about the particle nature of dark matter by linking large-scale cosmic observations to fundamental physics. The team is working on a three-dimensional map that will show not only where dark matter is in the sky but also how it is distributed in depth across cosmic distances. This will provide a time-lapse view of cosmic structure formation by revealing how dark matter structures have evolved over billions of years. What makes this discovery particularly powerful is the combination of scale and resolution. Previous dark matter maps covered large areas but lacked fine detail, or showed fine detail but only in small regions. Webb's map achieves both. It covers an area about 2.5 times the size of the full moon as seen from Earth, large enough to reveal the large-scale structure, and resolves features with twice the clarity of previous maps. Assessing this achievement, Diana Scognomilio emphasizes continuity with previous work. 20 years ago, Hubble provided detailed images of the cosmos field. Now, by overlaying Webb's data onto Hubble's, we can validate previous analyses and discover new features. Hopefully, in 20 years, my students will be able to create an even better map. Dark matter's invisible web is no longer invisible. Thanks to gravitational lensing and Webb's extraordinary capabilities, the universe's hidden structure has become observable. We can now see the structure that shapes everything: galaxies, stars, planets, and ultimately, us. The nature of dark matter remains mysterious, but its effects are becoming clear with unprecedented detail. Each new observation brings us one step closer to understanding how the cosmic structure actually formed and how the invisible majority of the universe plays a role in making everything visible.